Good morning.
Morning.
And so far, any questions, guys? Yep. Okay. Now let's just see if we can do the questions at the back of the book from chapter number 10. Okay. And yes, okay, at the same time, discuss a little bit about it. So we go to page 477. And it's going to be question 259. 58, sorry. Yeah, okay. So axial resolution describes the accuracy related to visualizing two structures that are dashed to the sound beam's mean axis. Now, please, guys, as I said, if this here is okay, it was a sound beam. This is the main axis of the sound beam. Okay. And that was going to be front to back. Okay, front to back. Or we could say it's okay, this one here will be shallow. This one here will be deep. Or let's say that okay, it's if for instance, okay. Look at it on a scan, it's going to be that this and this, right? Okay. Whereas now we can say, okay, if the beam goes here, it's okay. That's going to be the main axis of your beam. Did you guys get that? Okay. The answer parallel. Okay. So this would be as okay what they will call parallel to the beam's main axis. Okay. The answer would have been oblique if they had asked about the not oblique, sorry. What was it? Perpendicular. Had they asked about lateral resolution. Yep. So here's okay. Although I don't like this wording here, but it's okay. It's going to be parallel to the beam's main axis. Question 249. Now you are purchasing a diagnostic ultrasound system, System X. Okay, has a axial resolution of 0.7 millimeters. So it is 0.7 millimeters. Whereas X system D is 0.4 millimeter. Yeah, okay. Based on this information, which will produce the better quality picture. Okay. So we can mean it as, okay, what they mainly mean by a better quality picture is going to be, which is going to have the best resolution. Okay. Where these numbers here, respectively, were the numerical values of your exit resolution. Clear? Okay. Did that make sense? Okay. So this system here is okay as long as there was a distance of 0.7 millimeters between two structures. It will give you a good exit resolution. Whereas for this system here, it's okay, this is going to be as okay able to display two structures separately, even if there only was a distance of 0.4 millimeters. So this here have the lower numerical value. This one here has the greater numerical value. And greater numerical value is going to lead to a poor resolution. Lower numerical value is going to lead to a good. Okay. Because this system here, let's say it's okay that if the distance, for instance, okay, between two structures was 0.4 millimeters, this system here is okay with its great numerical value would give us a poor resolution, whereas this system here still could give us a good resolution, even if the distance was 4 millimeters or 0.4 millimeters. Did that make sense? If the distance here was, for instance, okay, less than 4 millimeters, let's say it's okay, 0.3 millimeters, then okay, in that case, okay, this system will still give us a poor resolution. But compared to this system here, this system still have a better resolution due to a lower numerical value. Did that make sense?
Yeah.
Okay. What could I cause? Yes, okay. Let's say together. System D here to have that low numerical value of the exit resolution could be, yes, okay, either due to a less number of cycles per pulse that we called less ringing, right? And or because that's okay, a low wavelength. Okay, which means is okay, what I meant, okay, yes, a high frequency. And how do we get a low wavelength? Mainly it's okay by a thinner PCT. So a thinner PCT is going to give us, okay, a lower wavelength, which will cause the transducer to have a higher frequency. Did you guys get that?
Yep.
Okay. Question 260. The exit resolution of an imaging system is reported to be as okay 0.85 millimeters. It's okay, the exit resolution is 0.85 millimeters. at the beam's focus. Okay. Here, okay. What is the closest estimate of the system's radical resolution? Okay, at a location 5 centimeters deeper than the focus. Okay, guys, now look here. Here they mainly is okay through a lot of things. So this was your transducer with the beam, right? Okay. Okay. Now what they say is that okay, yes, at the focus, which we may be here, right? Okay. Let's say that this is the focus. At this point here is okay, our exit resolution is 0.85 millimeters. Did that make sense?
Yeah.
Good. But what they ask us is that, okay, as at a distance which is, let's say, 5 centimeters deeper than the focus, what do you think that the exit resolution is going to be here? Now, there was something that I told you guys regarding exit resolution. And if you remember that, you'll be able to answer. The exit resolution remains constant. So what does that mean? That even is okay at this depth here, the exit resolution is going to be the same, 8.5 millimeters. Is that clear?
Yeah.
Okay, okay. Now some of you will say, well, okay, doesn't the wavelength change as it travels through different medium? But that's not what is the case for your resolution here, because the exit resolution, guys, is going to be determined by the transducer. Okay, so the wavelength of the sound wave produced at the transducer level, that's going to mean it's okay, what we're calling for the numerical value of your exit resolution at no matter what depth. So even if you say that, okay, as what, oh, shit. Even if it asks, okay, as what is going to be the exit resolution at a depth which is, let's say, 5 centimeters shallower than the focal point. Even at this point here, it's okay, it will still have been the same 8.5 millimeters. That applies for your exit resolution. Okay. Whereas, okay, if they say it's okay, the lateral resolution. Now, lateral resolution, that was mainly, it's okay, its numerical value was the width of the beam. Okay, so if they, for instance, said that, okay, yes, at the focus, that the lateral resolution, let's say it's okay, the same 8.5 millimeters. Just for an assumption. But if they ask, okay, what is going to be, it's okay, the lateral resolution at a depth 5 centimeters deeper than the focus. While here, that lateral resolution is going to be greater than 0.85 millimeters, because here's okay, the beam is going to be greater than or more wide than 8.5 millimeters. Did that make sense? Like, yes, okay, since you see, yes, okay, they do not use the word axial resolution, they use the word radial resolution. So if you didn't know, yes, okay, the axial resolution also was called axial resolution, or radial resolution, sorry, you would have been lost. Did you guys get that? Okay, so although it's okay, it's a radial resolution, but you should mean it's okay, just be able to, you can translate that or convert that into axial resolution. Okay, it's the same thing. Okay, and then just apply your concept. Did you guys get that? Good. So what did that 8.5 millimeters, okay, 0.85 millimeters mean here? That as long as the distance between, yes, okay, two reflectors, shallow and deep, had a distance that was either equal to, yes, okay, 0.85 or greater than 0.85 millimeters, we will have a good resolution. Whereas, if this distance here, for instance, okay, had been lesser than 0.85 millimeters, you have had a bad axial resolution, sorry. Okay, guys, question 261, just skip that one because that is, well, okay. We can say it's okay here to talk about, that's going to be our contrast resolution, or, let's put it this way. Okay, means that's okay, the info that we are given here is, not going to be as okay relevant to calculate your axial resolution or longitudinal resolution. Okay, pixels and things like that, that's going to be as okay for our spatial resolution, which we'll talk about in chapter 15. So this info here doesn't give us any clue about lateral or axial resolution, sorry. Now true or false. 262. The lower the numerical value of longitudinal resolution, yeah, okay, the worse the picture. Now, worse the picture is probably not the best wording. Could I say as okay? Could I be says okay? Something like okay is worse or bad or degraded resolution. But that's going to be false because a lower numerical value, in this case, is okay for your longitudinal resolution, which is your EXA resolution. That lower numerical value is going to cause that you actually have a better resolution. Did you guys get that?
Yeah.
Question 263. And again, it's okay, true or false. Now, one way that a sonographer can alter the axial resolution achieved during an exam is to adjust the maximum depth of the image. That's false. Now, because it says, okay, if this, for instance, okay, or our maximal depth of image, let's say it's okay, 5 centimeters. Even if we, let's say it's okay, increase that to, let's say it's okay, 10 centimeters. Throughout, whether it was here or here, we have the same spatial pulse length produced by this system here. So since that's okay, your spatial pulse now remains the same, adjusting the depth, whether from 5 to 10 centimeters, from 5 to 6, or 5 to 7.5, whatsoever. Or the other way around. That's okay when it says okay, from 5 to 2 centimeters, or 2.5 centimeters, or 3 centimeters. That is not going to have an effect on your spatial pulse length produced by the, so, I know I was so eager today, to be produced by your systems. And since it doesn't have an effect on that, yes, okay, it's not going to affect your EXA resolution. Did that make sense?
Yeah.
Yeah. Question 264. Now, with a specific ultrasound system and transducer, the EXA resolution is invariant, and the sonographer can do nothing to improve it. And that's true. Here, the main is okay, try both your hands and legs. But I'm saying, well, okay, yes, you have the same system. Okay, but the actual thing that okay makes this whole thing here true is that okay, yes, you have a specific transducer which is not variant. You can't change it. Which mainly mean, well, okay, this here will produce a fixed spatial pulse length. Well, that's what you have. Which may cause okay, throughout yes, okay, your EXA resolution will be the same. And you can't do anything to improve it. Just think of, okay, having a system to which is, okay, there was a fixed transducer attached to. You couldn't even change it. So you pretty much are unable to do anything to just, okay, either improve or degrade your exit resolution. Did that make sense?
Yes. Yeah.
Good.
Yeah.
Next question is true or false. Now, shorter pulse duration, better picture. So shorter pulse duration. Do you have a better picture? Now, guys, if you get a question like this, and okay, yes, your test, it should probably have said, okay, yes, better exit resolution. Now we can say it's okay for a better exit resolution. What do we need? We need a shorter spatial pulse length. And what we know is that pulse duration is directly proportional to spatial pulse length. Now, due to this lower spatial pulse length, so of course, yes, okay, that will lead to us, okay, lower numerical value of the exit resolution. Okay. So don't say it's okay, can't be determined. Because you mean it's okay, have to think of it in this way. How is it that these two fellows here are directly proportional? Whatever pulse we have, the pulse duration was determined by two things. One was number of cycles, which you also have, yes, okay, in the exit resolution. No, sorry, in your spatial pulse length. The second was period. Here is okay, that number of cycles was multiplied by the wavelength. And we know that period and wavelength are directly proportional. So the shorter the pulse duration of a pulse, mainly because, okay, that pulse will have a lower period, will also cause that will have a lower wavelength, will cause that you have a lower spatial pulse length, will cause that it has a lower numerical value of the exit resolution, which cause that exit resolution to be better or improved. Did that make sense?
Yes.
Good. And or this lower part period here, Comanias, okay, also means that we have a greater frequency. Or likewise, lower wavelength also meant that we have a greater frequency. Did that make sense? So a similar question can be asked as, okay, does a high frequency, does that improve your exit resolution? Does a high frequency transducer, does that have a better exit resolution? Yes, because it has a lower wavelength, right? Clear, okay, and a lower wavelength will lead to a better exit resolution. Okay, guys. $266. Now, ultrasonic pulse has a pulse repetition period of 1.2 milliseconds. Yeah. The spatial pulse length is 2 millimeters. Good. And a wavelength of 0.4 millimeter. Okay. Okay. What is the exit resolution of the system? Yeah. Okay, guys. Now, please. In this case, is okay. What they tried to do was to confuse you with this number here. And this. You mainly as okay didn't need all these two numbers here. The only thing that we needed was this, because okay, the exit resolution of your system is mean that's going to be as okay the spatial pulse length divided by 2. So that's going to be 1 millimeter. Is that clear?
Yes.
Because this number here is okay to change. Let's say that we want to decrease it. How do we decrease this number? How do we decrease the pulse repetition period?
Decrease the depth.
Decreasing the depth, exactly. Clear? Okay. That's pretty much it. So this number and this number here is okay was mainly is okay just to confuse you. Now, guys, never say never, okay? Because let's see if you guys know how to do it. It says, okay, you have a spatial pulse length of 2 millimeters. Clear? Right? And I say, yes, okay, you have a wavelength of 0.4 millimeters. But then I ask you, number of cycles in the pulse is what? I might even have given you, yes, okay, the spatial net pulse repetition period. Yes. Anybody who is able to tell me how many cycles did we have in a pulse?
Five.
5. Exactly. Okay. Question number 267. Now, the more cycles there are in a pulse, the greater detail will be visualized by the ultrasonic scan. True or false? That becomes false. Because you can say, it's okay, the greater number of cycles. What would that lead to? A greater spatial pulse time. Greater spatial pulse time leads to, okay, greater numerical value of axial resolution. And that will lead to or is okay, because it's okay, less details. Did that make sense? All this, okay, the word here, less details is probably not the best option. Or greater details, sorry. So greater details, that's what makes it false, because due to a greater numerical value, it's okay, we will have lesser details or more accurately, it's okay, because it's okay, poor axial resolution. Because it will not be able to distinguish closer structures to this. Yes, okay, greater details. It doesn't, in this case, yes, okay, it doesn't really specify in which resolution that it's talking about. Okay, so if you get a question like this on the exam, yes, okay, well, mostly yes, okay, specify I'm talking about, yes, okay, an axial resolution or lateral resolution. But just keep in mind, guys, okay, the more details you get, the deeper trouble is it that you are in. Okay? Not trouble in the bad sense, but it's okay, then you really have to be on top of your, yes, okay, concepts. Now let's look here because, okay, let's see, here's a question with a lot of numbers. Question number 268. Now, two ultrasound systems produce acoustic waves, or acoustic pulses. Okay, good. A pulse from system one. So what do we have? Has a wavelength of 0.5 millimeter. Right, okay. 4 cycles per pulse. And a pulse repetition of 1.2 milliseconds. Okay. The pulses from system 2 has a wavelength of 1 millimeter. So we can say it's okay. System 2, now what do they have? A wavelength of 1 millimeters. 2 cycles per pulse. Okay. And a pulse repetition period of 1.8 milliseconds. Yeah, okay. Now, which ultrasound has the lower numerical value of the exo resolution? So they're asking us which has the lower numerical value of exo resolution between these two systems here. Now, guys, just keep in mind, these numbers here are mainly as okay to confuse you. You may say, okay, some people may say, okay, as period or pulse repetition period is related to period, which is not the case. And choose mistakenly that, okay, as greater period will lead to as, okay, greater numerical value of spatial pulse length, and so on so. Because the actual data that you may as okay just needed from this question here was these two here. So what remaining can say is okay is going to be as okay the numerical value of exit resolution for system 1 would be 0.5 multiplied by 4, which gives us okay as a spatial pulse length of 2 millimeters, which then is halved, and we have a spatial pulse length of 1 millimeter, or a numerical value of 1 millimeter. Now, guys, as we go for the next system, which is system 2. Well, okay, we have a wavelength of 1 millimeter, and we have 2 cycles. That gives us a spatial pulse length of 2 millimeters, which again is okay, just divided by 2. And the numerical value is going to be 1 millimeter. So both of them have okay as the same numerical value. Did you guys get that?
Yeah.
Right, okay. So don't get thrown off by this, by these two numbers here, sorry. and say, well, okay, it's greater period. Or okay, it's chaos, okay, a greater numerical value. And okay, yes, this lower here is going to give you, yes, okay, this. Because pulse repetition period is not related to period. Yeah. So that's okay. Sometimes yes, okay, numbers may just be given there too, is okay, throw you off. So that's okay. Here, both systems had the same exit resolution. Because they end up having the same numerical values of exit resolution, which was 1 millimeter. Okay. Now, which 269. Now, which transducer has the best exit resolution? So best exit resolution, we can mean this as okay, well, if it has the lowest numerical value of exit resolution, which we know equals to spatial pulse length divided by 2. Which mainly will mean that, okay, yes, we will need to look for the one that gives us the lowest spatial pulse length. Okay, now what are going to be the true factor that gives us a low spatial pulse length is going to be a low number of cycles and a low wavelength. Yep, okay. Now what do we have? We have 2 cycles, 4 cycles, 4 cycles, and 2 cycles. So the one thing that we can do is take out the 4 cycles once, because that's high number of cycles. Okay. The next thing that we have is, now we don't have wavelengths, but rather frequencies. Okay. And we mainly say, okay, well, we need a low frequency, a low wavelength. Well, low wavelength is going to mean that will mean a high frequency. So the main one that we mainly have to choose between the two with 2 cycles per pulse is going to be the one with the high frequency, where we have 4 megahertz and 2 megahertz. So this 4 megahertz transducer here will have a low wavelength. Compared to, yes, okay, this other one here, which was okay, a low frequency, that will have a greater wavelength. Did you guys get that? Any
Yes.
questions? Okay. Now question 270. Now which transducer has the worst exit resolution? Oh, that means, what do we mean by worst exit resolution? Is going to be highest numerical value of exit resolution. Now what do we need for a highest value of exit resolution? Is going to be, means, okay, greatest number of cycles and or greatest wavelength. That will lead to us, okay, these will lead to us, okay, a greater spatial pulse length, which will lead to a greater exit resolution, a numerical value of exit resolution, which will cause exit resolution to be the worst. Okay. Now, as a matter of fact, that's okay. What do we have? 2 cycles, 4 cycles, 4 cycles, and 2 cycles. So 2 cycles, 4 cycles, 4 cycles, and 2 cycles. So here again, yes, okay, you can mean, yes, okay, just cross these two out. Because these are low number of cycles. So we're left with 4 and 4. Okay. Now what do we need? Greater wavelength. Now we don't have wavelengths, we mainly have frequencies. So greater wavelength may mainly mean that, okay, yes, we have to look for the one with the lowest frequency. And what are the frequencies we have? We have 4 megahertz and we have 2 megahertz. So this dude here will be the one with the worst, because due to a lower wavelength, a lower frequency, it will have a greater wavelength and a greater number of cycles, greater spatial pulse length, greater numerical value of exit resolution, greater numerical value, the worse the resolution. Did you guys get that?
Yes. Two ultrasound system produces pulses. Okay, so we have 2 systems. We can say 1. I guess we have system 2, 1 and 2, for instance. Okay. Okay, 1 pulse is 0.4 microseconds. That's okay. What they're giving us here is, okay, yes, the pulse duration. So that's okay, 0.4 microseconds. In duration, and the other is 0.2 microseconds long. Which pulse is most likely going to produce the best radical resolution? And radical resolution was also what we call the exit resolution. Clear? Now, although what we don't have here is we don't have a spatial pulse length. We can't say it's okay what the spatial pulse length is. But as we said earlier, that this and this are directly proportional. Likewise, this and this was directly proportional, which when you mean the one with the greater spatial pulse length is going to have a greater spatial, the one with the greater pulse duration is going to have a greater spatial pulse length, where the one with a lower pulse duration has a lower spatial pulse length. Okay, where this will lead to a greater numerical value of radial resolution or range resolution, where this here will have a lower numerical value of range resolution or radial resolution. But what they ask us is, okay, which is going to be the best? Best would be the one with the lower numerical value. So it's going to be this fellow here. Did you guys get that?
Yeah.
So don't say can't be determined. Clear? They just asked the opposite, then it would have been the one with the greater postulations. Had it said worse axial resolution or radial or longitudinal or depth resolution, okay, then it would just have been the one with a 4 microsecond pulse duration. Did that make sense? Clear? Okay. Now, it could have been non-determined if we had said period and not pulse duration. Then you can say, okay, it can't be determined. Because the period just tells you, okay, what the period of each cycle will be. But based on that, you can't say whether you have a long pulse or short pulse. Because a long pulse may still have, okay, as a short period because there was a greater number of cycles. Did that make sense? Okay. Okay, question number 277. 272. Now, a sonographer is performing a study on a patient and desires superior depth resolution. So he says, okay, he or she wants a superior depth resolution. Now, what superior here mainly would just mean is better. Here, okay. Now here they may use the word depth resolution or depth resolution. It was just another name for your axial resolution. Don't think that this superior depth resolution here is not going to mean seeing things at a shallow depth. Yeah, okay. Okay, because some people may confuse superior by superficial, which is shallow. Or shallow depth. So please do not confuse those. Okay. Which of the following changes will it create such a system? Okay. So our thing here is, okay, to get a better exit resolution. Now, how do we get a better exit resolution? We can say, okay, that is going to be either by having less number of cycles per pulse, and are those pulse cycles having, okay, as a low period, which will be equal to, yes, okay, saying that we have a lower wavelength, which will be the same as having a great frequency. Did that make sense? Clear? Okay. These here will give us a better exit resolution. Now, higher frequency, that's what we have here. Shorter wavelength, that's what we have here. Fewer cycles per pulse, that's what we have here. And less ringing, that's what we mainly just meant by fewer cycles per pulse. So in this case, it's okay, all the options that we were given were going to just, okay, give us a improved or better exit resolution. Did that make sense? So lesser number of cycles and less ringing. Maybe that's okay, or just two terms for the same thing. Did you guys get that?
Yes.
Okay, guys. Don't know Dina Slash. $273. Well, true or false? The higher the frequency of cycles within a pulse, the lower the numerical value. And that's true. Because what do we mean by higher frequency? Where mainly as okay is inversely proportional to the wavelength, which means that the wavelength will be lower. And when the wavelength is lower, your spatial pulse length is lower. Spatial pulse length is lower, the numerical value of your exit resolution is lower. Did that make sense?
Yes.
Good. So you are able to just, okay, tang, 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 dots like these. That's okay. There should be no reason why you shouldn't be able to answer it. 274 again, yes, okay, true or false. So shorter pulse length. Now here the main is okay, intention is okay, said lower pulse length. Gives, okay, yes, better picture. Okay. Now actually it's okay, not an ideal wording because okay, what do you mean by a better picture? Okay. Because okay, here by better picture is okay, when I talk about in terms of okay, as letter resolution, then that'll be false. Because the pulse length is not going to be related to your letter resolution. Okay. Well, it's okay, yes. So here's okay. Practically, yes, okay, this should have been yes, okay, better exit resolution. And then we could say, yes, okay, this is true. We know that I talk about exit resolution here because, okay, these were all questions about exit resolution. But if you get the same question as, okay, in the exam, worded like this, you may not know which resolution is it that they're talking about. Did that make sense? So hopefully at that point, yes, okay, it should have been more specific. Any questions, guys? Nope. Okay. Now just take a short 10 minutes break, and when we come back, yes, okay, we will look at the questions of letter resolution and focusing. Okay. So I see you guys, okay, should we say at 10:30? Okay, guys. So far, any questions? Okay, so we can see that's okay. Our next set of questions is about letter resolution and focusing, which both are, yes, okay, we can say it's okay, related to the beam. And what was it that a beam was? This, for instance, okay, will have been a beam, right? Did that make sense? Okay. So question number 328. Then you'll find on page 492. Now the focus of an ultrasound beam is the location where. So what the mean is, okay, just ask us, okay, where do we find the focus? Where is that? Now we know from our discussion when we talked about the beam is as where the beam is at its narrowest. Which mainly called as option A, which says broadest, is not the right one. Okay, optimum transverse resolution. Or transverse resolution was also another name for lateral resolution. And where optimum mainly is best. So that be the focus or the focal point be the point where we have the best lateral resolution. Yes. Because this lateral resolution here was going to be equal to the width of beam. I guess the numerical value of lateral resolution was the width of beam. So narrowest width at the focus, lowest numerical value of lateral resolution, which will cause it to be the best. Frequency is highest. Okay, your frequency remains the same whether it was here. So that has nothing to do with your focus. Finest depth resolution is obtained. Now again, yes, okay, if you do not know what we meant by transverse resolution versus depth resolution, yes, okay, you will be lost. Did that make sense? Because depth resolution was just another word for your exit resolution, which will remain the same at all points. Not only necessarily at the focal point, but the focus. So if you knew that focus, yes, okay, was the point in the beam where the beam was at its narrowest, and that will give us, the lowest numerical value of your lateral resolution, which was another name for your transverse resolution. And lower numerical value gives us the best. That's how it's you get the answer of, question 200 and, it's 328. Did you guys get that?
Yeah.
Question number 329. Now, lateral resolution of an ultrasound system is primarily determined by the. Now, I don't agree really with the wording here, because it was actually not going to be the width of pulse. That's the wrong wording. The actual wording would have be the width of the beam. Okay. So if it was up to me, yes, this answer would be wrong. Did you guys get that?
Yeah.
Question number 330. Two ultrasound systems produce acoustic pulses. Now what have they given us here is, we can say it's okay, two systems, so we can just name them A and B. Now one pulse is 0.4 microseconds. So what have they given us? A pulse duration of 0.4 microseconds. And the other is 0.2 microseconds. Okay. Which pulse was most likely produce the best lateral resolution? Now here it's okay, we can say it's okay, this can't be determined. Because for the lateral resolution, what was it that we needed? Width of beam. Clear, okay. Now both of these pulses here can have, yes, okay, the same width, or they can have, yes, okay, different widths of the beam. We don't really know. Did that make sense?
Yes.
Good. Question number 331. And a matter of being true or false. Now pulse duration, oh, that's okay, the pulse duration does not profoundly influence the lateral resolution. And that's where we say true. We just set it up here as well, right? Okay. That this value or this value here really can't determine the lateral resolution. Why? Because pulse duration is not related to your lateral resolution. Did you guys get that?
Yeah.
Good. Question number 332. Two ultrasound systems have a near zone length of 8 centimeters. So we can say, okay, we have two systems, A and B. Now, what do they say here? Is okay, both have a near zone length of 8 centimeters. So we say, is okay, this here is okay, was our beams. For both systems. We can mainly say that they both have a near zone length of 8 centimeters. Okay, now I need to give us numbers. Okay, so we say it's okay, system G. Sorry. I'll probably a little bit too quick on the trigger here. Lateral resolution is 3.8 millimeters, 3 millimeters. So we can say, okay, here, for instance, that maybe is okay what we'll talk about. 3 millimeters. Whereas system P as in Peter has a 5 millimeters. Lateral resolution. which system will produce the higher quality focus or higher quality picture at the foci. So that's okay. That's what I was talking about. So this is the width of the beam of system G at the focus, 3 millimeters. And this is the width of the beam of system P at a depth of 8 centimeters or at the focal point. So we can mainly say, okay, this beam here has a narrower width, whereas this beam here has a greater width, which becomes just okay a lesser numerical value of lateral resolution and a greater numerical value of the lateral resolution. Okay. Although it's okay, I don't like the word higher quality because resolution is not really about quality, it's more about accuracy. Okay, since they use that, we can say, okay, lesser numerical value is going to be better lateral resolution and vice versa. Greater numerical value is going to lead to a poor resolution. So here it's okay, it is system G that has the better resolution, whereas P as in peanut has a poor lateral resolution. Did that make sense?
Yes.
Question 333. When using standard ultrasound imaging and instrumentation, the lateral resolution has a higher numerical value than the axial resolution. Is that true or false? So what we mainly say is that, okay, as does lateral resolution compared to axial resolution. Have a greater numerical value than that of axial resolution? That was true. And what we due to that, that's why we say that, okay, as lateral resolution is poorer and axial resolution is better when we compare these two resolutions here against one another. Is that clear?
Yes.
Good. But, guys, please, there is going to be a okay exception where these numerical values here are the same. Okay, where the numerical value of lateral resolution equals that of axial resolution. And of course, that's okay. If they equal, then yes, okay. No, okay, no, sorry. Sorry, please. Disregard that. That will be another resolution. Okay, but generally speaking, it's okay when talking about axial resolution versus lateral resolution. Axial resolution always have a lower numerical value, whereas lateral resolution always have a greater numerical value. So lower the numerical value, better resolution. Higher numerical value, poorer resolution. Did you guys get that?
Yeah.
Okay. Question number 234. Oh, sorry. 334. Okay, good. So again, yes, okay, two ultrasound systems, yes, okay, have a focal length of 8 centimeters. On yes, online. So before we go, yes, okay, system Q and H. Okay. And what do we have? Yes, okay, of course, it's okay, we have a beam, and a beam, and a beam, and a beam. And what do they both have? Yes, okay, they both have, yes, okay, the same focal length of 8 centimeters. Now, lateral resolution of system Q is 3 millimeters. And lateral resolution of H is 5 millimeters. Yeah, okay. Which system? Now, which system will correctly display two small structures at a depth of 8 centimeters? The objects are side by side and 0.4 centimeters apart. So what they mainly say is that, okay, as we have two structures, now they're going to be up at this depth here, but just so it's okay, we say, make okay as a common, that the distance between them is 0.4 centimeter. Okay, now please keep in mind that, okay, that 0.4 centimeters equals to 4 millimeters. So if the distance between, yes, okay, two structures which were side by side was played also, okay, as at a distance of 4 centimeters or 0.4 centimeters from one another, which of these two beams here will give us a way as, okay, clearly display those two structures. So here is for the width of your beam, 3.4 centimeters, 3 millimeters, and the distance was 4 millimeters. So here is okay. Okay. These two structures would appear clearly where here the width of the beam was 5 millimeters or 0.4 centimeters, where the distance between the two structures was 4 millimeters or 0.4 millimeters or 0.4 centimeters or 4 millimeters. So here they will appear as 1. So system Q will be as okay, able to show us these two structures here, which were side by side, as two structures, where this system here will show it as 1. Clear? Okay. How and why? Here we can say it's okay that the numerical value was lesser than the distance between the two structures. Whereas here, our numerical value was greater than the distance between the two structures, which were side by side. Did you guys get that?
Yeah.
Okay. Any questions?
No.
What things to look for is that, okay, they say the structures were side by side. Had they said structures, being shallow and deep. Shallow and deep. Then it was not going to be the width of the beam that will determine whether we see them as two separate echoes or have a good resolution. That was going to be as okay. Your spatial pulse length that will determine that. Okay, where that has to yes, okay, be divided by 2. And if that number that we got here was lesser than the distance between the two structures, front to back or shallow to deep, or parallel to the beam's main axis, then we will have a good resolution or good axial resolution. As okay, if that numerical value was greater than the distance between the two structures, front to back, shallow to deep, or parallel to the beam main axis, then we will have a poor axial resolution. Did you guys get that?
Yes.
Now, question number 335. Now, the lateral resolution of an ultrasound is 4 millimeters. We can mean says, okay, we have a transducer. Okay, it produces a beam. Okay. That mainly will say, okay, it has a lateral resolution of 4 millimeters. Probably that's okay. We could assume for now that, okay, yes, that's going to be lateral resolution. And we can say, okay, will be 4 millimeters, which was going to be as okay, the distance between these two structures here is okay, side by side. Okay. Okay. What is most likely going to, okay, let's see. Lateral resolution, and okay, yes, no, okay, no, okay, good. As a lateral resolution. So that was going to be a 4 millimeters. So this 4 millimeters here is okay, that's going to be the lateral resolution, which was going to be as okay, the width of the beam. Now what they say is that, okay, yes, if the, okay, two structures are separated by 3 millimeters. So we have two structures where the distance between these two here was 3 millimeters. Okay, what will most likely appear on the system's display? How are these going to, yes, okay, appear on your image? Now, what we mainly can say here is, okay, that the lateral resolution's numerical value that is greater than the width between the structures. That's why the system mainly is, okay, will not be able to, yes, okay, distinguish these two. So these two structures, yes, okay, are going to appear as one echo or one reflection on your scan. Although, yes, okay, we had two structures, and due to that, that will mainly, yes, okay, mainly mean that, okay, yes, we have a poor lateral resolution. Did you guys get that?
Yes.
Clear? Okay. Had the beam been 3 millimeters and the distance ever been 3 millimeters, then we are seeing two structures at a distance of 3 millimeters apart. But mainly as, okay, you see that, okay, the numerical value or the width of the beam is greater than the distance between the two structures which are side by side. That's going to cause that we have a poor axial resolution, lateral resolution, sorry. Did that make sense? But, please keep in mind, guys, that this says, okay, that these two structures, yes, okay, had been placed at at the same distance of 3 millimeters, but parallel to the beam's main axis. Then in this case, yes, okay, you are seeing these two structures, yes, okay, placed like this at a distance of 3 millimeters. So you have had two echoes at a distance of 3 millimeters. But this was going to be your axial resolution. Okay. Now this would be provided that, okay, yes, your spatial pulse then was 6 millimeters or less. Did you guys get that?
Yeah.
Yeah.
Question number 336. And again, true or false. Now, when using an instrument, typical of today's imaging devices, a higher frequency transducer is likely going to mildly improve the system's lateral resolution. Now, higher frequency. What did we say that led to? Lesser beam divergence. Did you recall that? the frequency was inversely proportional to the divergence of the beam. Well, that means that, okay, yes, for instance, okay, we can do it this way and say, yes, okay, we have lower frequency that will cause greater divergence of the beam. So we had a transducer. We're not going to go into the focal depth of it. Let's assume that, okay, yes, it would have been the same. But if this transducer here had been, okay, as a higher frequency transducer, that would have been, okay, as a lesser degree of divergence of the beam in the far zone. Contra to, yes, okay, a low frequency transducer will have greater divergence of the beam in the far zone. So what that actually means is that, okay, yes, a high frequency transducer has lesser divergence of the beam, where you can mean it as, okay, the lesser the beam diverges in the far zone, well, okay, yes, better lateral resolution, whereas, okay, yes, this low frequency beam has a greater divergence, and that greater divergence of the beam actually is, okay, leads to a greater beam diameter, which is going to be as, okay, a greater numerical value, which will lead to as, okay, a poor lateral resolution. Did that make sense?
Yes.
Okay. So again, yes, okay, one of the main reasons that, okay, yes, high frequency transducers are ideal for diagnostic imaging. Question 337. Again, yes, okay, true or false. Let's just give that. False. Now, when using an instrument typical of today's diagnostic imaging devices, higher frequency transducers likely improve axial resolution. Okay, that was again true. Higher frequency leads to lower wavelength. Lower wavelength, lower spatial pulse length. With lower spatial pulse length, lower numerical value of axial resolution. And this lower numerical value of the axial resolution leads to, yes, okay, a better axial resolution. Did you guys get that?
Yes.
What will lower the value of an ultrasound system's lateral resolution? Now, what the meaning is, okay, mean by the value here is the numerical value. Now, decreasing the number of cycles in the pulse, no, that's going to just, okay, reduce the numerical value of axial resolution, not your lateral resolution. Increase the effective damping material. Now, that is also just going to just, okay, reduce the frequency. Yeah, okay. Increase the pulse repetition period. Now, pulse repetition increase your pulse repetition period. Now, that has no effect on your axial resolution or your lateral resolution. So use an acoustic lens. Now, to be more specific, yes, okay, because yes, okay, reduce the size of the acoustic lens. Okay, how would I do? Reduce the width of beam. And reduce of width of beam will reduce the numerical value of the lateral resolution. Did that make sense? Why? Because, okay, PCT diameter was directly proportional to was it proportional to divergence. Or to begin with, smaller PCT versus greater PCT produce narrower beam, wider beam. Okay, guys?
Yeah.
Okay, question number 339. Which of the following focusing technique is different from the others? Lens, curved crystal, fixed or phased? Now, whether we said, sorry, when we use a lens, that was, okay, as external fixed focusing. If we said curved PCT, there was internal fixed focusing. When we say fixed, that because we only had, okay, as one fixed focal point. Whereas if we say phased, okay, where we say phased, we mean is, okay, we mean phased array, which means multiple focal points. So what were these? These were all fixed focus, where we mean is, okay, we're just able to focus at one fixed point and not changes, which we were able to do in phased or phased array transducers. So this phased array phase, that was going to be the one that doesn't belong to the group. Otherwise, it was all just talking about as okay, fixed focal points. Did you guys get that?
Yep.
Good. Question number 340. Which of the following technique is an internal focusing? Our internal focusing guide, that was when we had curved PCT. That one of the surfaces of our PCT was curved like this. That was when we had an internal focus. Whereas, okay, as in 341, where they just talk about external focusing. Now that was when we had a lens. There we says, okay, we had the PCT, but in front of the PCT is okay, external to the PCT is okay, we had a lens. Where was going to be the lens that was curved. Did you guys get that? Now, question next to 42. Which of the following term means adjustable focusing or multifocusing? And that's why I say it's okay, phased array. Where practically it's okay, the word array will mean multiple focal points, or able to focus at multiple depths. Dynamic aperture, now what you will see in chapter 12. It okay, yes, a dynamic aperture may improve, yes, okay, the resolutions at multiple depths or at multiple focal points. Okay, that's why they put it in there. Chapter now, okay, harmonics, yes, okay, there's a hell of a chapter. 17, which just talks about harmonics. And frequency and agility, that's probably not something that we'll be talking about. So for now, yes, okay, but what the term array or phased array will mean, that we are able to focus at multiple depths. Now, which 343, which of these techniques is consistent with a variable or multiple or multifocusing? Now, what we said, okay, this phased array was, or phased array or array focusing was, is going to be electronic. Okay. So, although yes, okay, the shape and size of our PCTs, even yes, okay, these transducers here, it's okay, don't change. But the way that they will be able to just, okay, focus not at just one, but at multiple points is going to be as okay, controlled or regulated by the electronics of the system. Okay, something that we will briefly talk about in chapter 14. So most of all of our SOK array focusing is going to be electronic. Clear? Now all of the following SOK will occur at focusing except from. So we have a list of things that SOK will occur at focus, but we have to pick up the one that doesn't fit into. So at a focus, do we have a lower intensity? No, rather vice versa. At a focus, what happens? There's going to be SOK where there's an increase in intensity due to that narrow diameter. Did that make sense?
Yes.
In which region of a sound beam is the focusing most effective? So let's just look at a beam. And see it's okay. Which one is it that they mentioned here? So this, for instance, okay, here is our beam. The very shallow near zone. Do we have a good focus here? No. The end of the near zone. Do we have a focus here? Yes. Very deep in the far zone. Do we have a focus here? No. Throughout the entire length. Is that where we have the focus? No. So maybe it's okay, just a question about it's okay, the beams anatomy. Did that make sense? True or false? In comparison to other locations along the ultrasound beam, focusing is generally ineffective in the far zone. Yes. Because, okay, what happens to the beam in the far zone? That's where it starts to get around. Where we can mainly say, okay, here, focusing improves. But here it's okay, it starts to degrade. Yep. Question 347. And again, it's okay, we have two systems. C and S. Now, two ultrasound systems have near zone lengths of 8 centimeters. Okay, let's just draw the beams first. Yeah, okay. So again, it's okay. We don't have a diagram, but we mean it's okay, just have words. So it says, okay, the near zone length is 8 centimeters. Now at the focus system aid has a lateral resolution of 3 millimeters. And system C, okay. Let's see. System S, okay. S and C. And system C has a lateral resolution of 5 millimeters. Okay, which system is most likely going to appropriately display two structures that lie front to back in front of one another at depth of 8.6 centimeters, 8.6 millimeters, and 9 millimeters. So what we have here is two structures that are front to back of one another at a depth of 9.6 millimeters. And this here is at a depth of 9 millimeters and 8.6 millimeters. And guys, here can't be determined. Did that make sense? Because here's okay, they gave us the different depths of two reflectors. Not the distance between them from side to side. Had it been side to side, then we could have said, yes, okay. If it says, okay, at a depth of 8 centimeters, if the distance between them was so and so, that because it's okay. Okay, yes, okay, here is, or if you can't just, okay, subtract it, that's what I mean is, okay, where you say, okay, this one here would have given us, okay, as a good resolution, whereas this one here would have given us a bad resolution. Because you didn't look at the thing that says, okay, that this was the width of the beam, and this is, okay, the depth of the what you want to call it, of the reflectors. Did that make sense? So here is okay, this was mainly is okay, these numbers here were mainly is okay, just to confuse you. Whereas if you said, okay, but if the distance had been yes, okay, as had been side to side, and we had a distance of okay as 4 millimeters and 4 millimeters, then of course, okay, this would have given us a better resolution, but that resolution would not have been yes, okay, that they were side to side, okay, front to back, but rather side to side. Okay. And that side to side then never had asked about a lateral resolution. Did you guys get that?
Yeah.
Right, okay. Because I said that if this system here have had, okay, yes, a spatial pulse length of, let's say 4 millimeters, and this one had a spatial pulse length of, let's say it's okay, 10 millimeters. Then this would have given us, okay, as a poor axial resolution, where this would have been a good axial resolution. Because here it's okay, it will become 5 millimeters. Here would have been 2 millimeters. That these two reflectors then would have been appearing, yes, okay, separately. Or we could have seen them as distinguished two reflectors, shallow or deep. So guys, I can't emphasize this enough. Watch out for those things, okay? Front to back, shallow to deep, or side to side. Clear, okay? The info that you are given is okay as the spatial pulse length, or whether that's the width of the beam. Spatial pulse length is okay, half of that will apply to your lateral axial resolution. Width of beam exactly would apply to the lateral resolution. Did you guys get that? Okay, girls. Guys. Question 348. Oops. What the blue? The diameter of a disc-shaped unfocused piezoelectrical crystal is 1 centimeter. What is the best estimate of the minimum lateral resolution of this system? This is me just asking what's going to be as okay the diameter of or the width of the beam at the focus. This width here equals to half of this width. So what's the half of 1 centimeter? Is 0.5 centimeters or 5 millimeters. Did you guys get that?
Yes.
Now let's see. Now the diameter of a disc-shaped unfocused piezoelectrical X, okay, is 1.2 centimeters. So again, it's okay. This is our PCT, sorry, and it's 1.2 centimeters. The near zone length is 8 centimeters. Okay. So you say, okay, this is the focus, and what they mean is, okay, they'll say that this distance here is 8 centimeters. I don't know what it's about this book here. It's okay, focal depth of 8 centimeters. Anyways, okay, what is the best estimate of the lateral resolution at a depth of 16 centimeters? So again, it's okay, what they ask us is okay, what's going to be the lateral resolution here, which becomes just okay, which is going to be at a total depth or total distance of 16 centimeters. And pretty much, okay, that's the same as what we have done in, okay, this question when we talked about the beam. It is going to be, it's okay, 1.2 centimeters as well. Because twice the focal depth. Did you guys get that?
Yes.
Any questions? So what are some golden words that you have to look for? Front to back, shallow deep, parallel to beam's main axis, or mean the same? Well, with those distances determined, exit resolution related to half of your spatial pulse type. Clear? Okay, where you say it's okay, side to side. Well, with that determine your lateral resolution. Okay, or we can say it's okay, it should be compared to the width of the beam. Did you guys get that? Have you guys heard the story of a poor lateral resolution? There's a sick joke about poor lateral resolution. Never heard of it? Okay. Now, there was a guy who was driving down the street on a motorbike. Clear? Okay. And it's dark street, there's no street lights, nothing. So you made it, okay, just drive on. It's okay, ride on with the help of your own headlight. Now he's riding a motorbike. Now what he see coming towards him is 2 headlights. Now since he was riding a motorbike, he thought that, okay, maybe 2 motorbikes are approaching me. And his thing was, wouldn't that be fun if I try to pass right in the middle of those 2 motorcycles approaching me. And that's what he tried to do. Now, the next thing that happens was he woke up in the hospital. And right next to his bedside were standing two people. One a doctor and one some random dude. And the doctor told him, well, okay, you almost got killed. But be thankful to this truck driver whose truck you ran into that he brought you to the hospital. Okay, so what's the moral of the story? Just because you're riding a motorbike doesn't mean that, okay, yes, two people in front of you will be riding a motorbike. But this guy still didn't get it, that he ran into a truck. He asked him two things. First of all, where's the other fellow that was riding the other bike? And the other question was, why did you guys put a big log in between the two bikes? Okay. Okay, guys. Now just take an early lunch break and I will see you guys back no later than 12:25. Okay? And we will start with chapter number 12. Now, before that, just make sure that you know your axis.
Are we skipping chapter 11?
Oh, sorry, 11, sorry. Yeah, chapter 11, sorry. Thanks, my dear. Chapter 11, okay. So please make sure that you know your axis, x-axis, y-axis, and z as in zebra axis. Capiche? Okay, thank you. Welcome back, guys. Okay. Sure. And so far, any questions?
No.
Chapter number 11. which is about display modes. Okay, guys. Now a couple of things. First of all, yes, okay, each of the 3 display modes that we were talking about, yes, okay, has a name. Which is going to be A mode, E mode, and M mode. Yeah, okay. So one thing to remember is that, okay, in A mode, what does A stands for? In B mode, what does B stands for? And in M mode, what does M stands for? Yeah. Okay. Now, guys, each of these modes here are going to just, okay, display the information along 2 axes. So we have to remember which axis is it that we were using and what is it that each of these axes here is okay represent. Okay. And then yes, okay, mean yes, okay, just some general info about each of these display modes, if that's what you want to call it. Did you guys get that?
Yeah.
So let us get one thing straight. Now, guys, when we say A mode, A stands for amplitude. B mean brightness. But what you guys will see later on is, or we're going to bring it up in this chapter here, is that, okay, this brightness here is actually going to also represent amplitude. Yeah, okay. Whereas as M, now guys, if you recall the other day, when I turned on the M mode, it says, okay, M must mean is okay, standing for motion. Did you guys get that? Okay. So A in A mode is for amplitude, B primary brightness, but this brightness actually is okay, will be the same as saying it's okay amplitude, and last is going to be M, which is going to be motion. Now let us just look at A mode. Now guys, as we said earlier, A mode stands for amplitude. Now what was it that we said that amplitude was? Mainly it's okay because it's okay the physical bigness of a wave will be as okay the amplitude. Okay. Now in this mode here, or A mode, what is it that we're going to have? Yes, okay, we're going to have yes, okay, 2 axes. We are going to have okay, what is our regular y-axis? And we're going to have as okay the x-axis. Did you guys get that?
Yep.
Now, in this case here, it's okay, guys. Just consider that, okay, yes, this is where your transducer is. It means says, okay, what is that the transducer? Now, let's do it this way. Let's do it. So, do it this way. I say it's okay. If this was your transducer, what did it do? It sent out sound waves to greater and greater depths, which were going to just okay produce reflections that will come back. Okay. Where we mainly says, okay, the amplitude of these reflections here is going to be expressed along the y-axis. So along the y-axis, what is that we're going to have? The amplitude. To be more accurate, we can mainly say, okay, it's going to be okay, the amplitude of the reflections. Whereas, okay, is where we have along the x-axis is going to be the depth. So guys, in both cases, whether it was depth, this is the minimum depth, and we can say, okay, 1, 2, 3, 4, 5, 6, and so on, so 7. Clear, okay? Millimeters, centimeters, whatever. Clear, okay? Which means that's okay, that's established at the point of okay, yes. This would have been yes, okay, where our transducer was. Sending out yes, okay, sound waves to different depths at a distance are going to yes, okay, get greater and greater and greater as we went along the x-axis. Whereas even for yes, okay, the amplitude, because yes, okay, this will still be the 0 point. And where we can say yes, okay, then the amplitude will just be bigger, 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 and bigger. Which we can say is okay. Let's say it's okay that from the shallow depth here, we receive a reflection with a strong amplitude. It's going to be okay, a big graph. Then we go like this. Then we can say okay, a weak reflection, something like this. So what did that tell us? That okay, as from these depths here, for instance, what did we get? We get yes, okay, reflections that had a big amplitude, and that's how it's okay, they're displayed by big vertical graphs. Where we can say, okay, between this distance here and this distance here is okay, what did we have? Waves with low altitudes. So that's why we just got these small zigzags here. Likewise, here's okay, small zigzags, small zigzags. Yeah, we can say, okay, what did we get from these depths here, for instance? As okay, amplitudes, or as okay, reflections with, or okay, not a strong amplitude, but not a weak amplitude either. Did that make sense? where you can say it's okay, these waves here is okay. At these depths, for instance, okay, overhead beam is okay. Something like this. Okay. So along your x-axis, the depth increases. Okay. But it's okay. Whereas, okay, along the y-axis, mainly it's okay. You can say it's all dependent upon the strength or the power or the intensity or amplitude of the reflection you get. You're going to have, okay, it's a bigger spike, yes, okay, displayed on your monitor. Did you guys get that?
Yeah.
Okay. So what can we say about these? As okay, had this been okay as a traditional image? These reflections here were had been bright. These here were had been darker. And because yes, okay, these here were had been the even darker. Whereas these were had been the darkest reflections. But stronger reflections, spikes with bigger amplitudes, weaker reflections, spikes with smaller amplitude, and okay, yes, the very, very weak reflections or no reflections at all. Yes, okay, no spikes, or if yes, okay, very, very small spikes. Did that make sense? Okay, so as it even says in the book, that okay, yes, it looks like okay, yes, the skyscrapers along, yes, okay, the skyline in the town, I'll see them. Did you guys get that?
Yes.
Now, please keep in mind, guys, here's okay, this depth here. Well, okay, that's going to be directly proportional to the PRP. And of course, that's okay, inversely proportional to PRF. Where, of course, that's okay, this amplitude is going to be as okay, directly proportional to the power and intensity. But please keep in mind, guys, that is going to be as okay, the power of the reflection. And okay, that intensity of the reflection. Now, as I said the other day, that okay, yes, we don't have this mode here on our systems. Okay. And why? Mainly as okay, because this A mode here, as we know it as, is mainly as okay, used for ophthalmology. Which is yes, okay, if you need yes, okay, scan, let's say it's okay, the structure of the eye. Did that make sense? Okay. So A as an apple. A in this case here means amplitude, where you mainly can say is okay, that what you get is mainly as okay, just going to be a graph with bigger or smaller spikes. Clear? Okay. You can say it's okay. The bigger spike is mainly because it is produced by a wave having a greater amplitude, whereas okay, as a smaller spike is going to be as okay produced by a wave with a smaller amplitude. Okay, but what is that these spikes is okay are going to represent is going to be as okay the amplitude of your reflections. Did that make sense? But literally, as okay, just going to be displayed in the form of a graph. And as you go on the x-axis along, okay, as you go on the graph along your x-axis, that's just going to be an increasing and increasing and increasing and increasing and increasing depth. So your x-axis displays the depth of the reflectors. Did you guys get that?
Yes.
Any questions?
No.
Now, okay, let's, okay, so now you guys may, yes, okay, see this. Okay, so this scan here, right?
Yeah.
Get just choose a color that's going to just okay stand out. Okay. So we can maybe that's okay, say that this here would have been our 0 point. This is your y-axis. And that's going to just okay indicate your amplitude. Whereas you can see it's okay, this here is your x-axis, and that's going to just okay represent the depth. Okay, so what do we see here? A big spike, and then okay, some smaller spike. Then we have okay, as a very big spike, and then okay, some relatively smaller spikes, and so on. Okay, by mania, okay, the bigger the spike, the greater the amplitude. The lower the short, the smaller the spike, the lower the amplitudes. Whereas, okay, as we go from here, like this, you can mean this as, okay, this direction here is going to mainly mean as, okay, that we are having an increasing depth. Okay, so yes, okay, at different depths, you will be able to just, okay, identify the intensity of the reflections produced by the structures. Okay, so this means that's okay, just a demo of your A mode. Did you guys get that? Now, guys, let's get back to our modes. And our next mode that we were talking about is going to be B mode. Did you guys get that? Now, guys, your B mode. Now, as I said earlier, B, the word B actually, as okay, stands for brightness. Yeah, okay. Now what we actually will see in just a little bit is that, okay, as what this brightness here actually is, okay, also will represent is going to be the amplitude. And just to be a little bit more specific than the book, I would say, okay, the amplitude of the reflection. Did you guys get that?
Yeah.
Good. Now, just like your A has an amplitude mode, B mode also have two axes. Okay. B mode also is going to just, okay, display its info along two axes. One of the axes is going to be, again, it's okay, the same x-axis. Okay. And in B mode, yes, okay, what the x-axis is going to represent is going to be the same as it did in your B mode depth. Is that clear?
Yep.
Good. Now B mode is going to be okay, a unique kind of mode in the sense that that's going to be the only display mode that use the z-axis. Is that clear? Is that clear?
Yes. Yep.
Good. Now, what the z-axis mainly is okay will display is going to be as okay the amplitude. Yeah, okay, but what we mainly is okay, we'll just say that this amplitude here is going to get directly translated into brightness. Okay. Now, guys, not something that you necessarily is okay need to understand, or it's okay to remember. But just think of it in this way, that what actually just okay going to move across your screen like this is going to be as okay an invisible dot. Clear? Okay. That invisible dot, yes, okay, when hit by the energy of a reflection, is going to spark up. Clear? Okay. Now, the magical trick here is the greater the energy that that dot is going to be hit with, it's going to appear brighter. Where, okay, the lower the energy that that invisible dot is being hit with is going to appear darker. Did you guys get that? Yeah, okay. So, what did that tell you? That along the z-axis, if you have, okay, as a high amplitude of a reflection, that's going to have a great brightness or appear bright. Whereas, okay, on the other hand, if we have a low amplitude of the reflection, that hits that invisible moving dot is going to just, okay, light up as a lesser bright or more dark. Did that make sense?
Yep.
So when I said back in chapter 6, the stronger the intensity of a reflection is going to appear brighter. Here's the logic behind it. Because that intensity of that stronger reflection is going to have a wave with a greater amplitude, which we in B mode just translate into more brightness, and vice versa. So a weak reflection, which is going to be as, okay, carrying less energy back, will have, okay, as a lesser or smaller amplitude. And that invisible dot being hit by a lower intensity, a lower amplitude, a lower energy is going to just, okay, spark up less and appear bright dark. Did that make any sense? Clear? Okay. So it will be correct to say that, okay, yes, your B, in your B mode, the Z-axis, Z as in zebra, displays both amplitude or brightness, because that amplitude is directly going to be translated into brightness. Did you guys get that? Okay. And it's directly. Greater amplitude, boom, bright spark. Lesser amplitude, lesser bright spark. Or you can say less brightness. And the least amplitude or no amplitude at all, no bright spark, no sparking, no light is, okay, okay, no light is turned on. What happens? Black. Did you guys get that? Okay. Now how we may, as, okay, play around with these or with amplitudes of the reflections to cause them to appear more and more and more bright, or less and less and less and less bright. We will talk about those details in chapter 14. Did you guys get that? Okay. Any questions? Okay. Now, please, 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 guys. I know, yes, okay, this may not make much sense. But it's okay. On your image, as you see it, yes, okay. This will be your depth. Okay. Anyways. Now we can just, yes, okay. Again, yes, okay, try to look at an image. Here. Can you guys see this picture here?
Yep. Yep.
It's what you may, yes, okay, figure out that, okay, yes. This here is, okay, the outline of a kidney. Clear? Okay. Now, you see the kidney here. Okay, let's just look here, guys. What did we call this area here?
The highlight.
Hilus. Clear, okay. So you can mainly say, as okay, in this case, yes, okay, this was the abdomen. Okay. And let's say it's okay that we were scanning a kidney. This would have been the kidney. And this part here is okay, will be the hilus. And what you see up here is mainly as okay, the footprint of your transducer remaining mean that okay, yes, the transducer in this case is okay, is being held here. So you can say this part of the kidney is what we have here. As we just go deeper. And deeper. And so. Did that make sense? Okay. But what do we see here? Now we can see it's okay. If you look at the kidney itself. Now what do you see here? Let's just make some bright colors. I'll choose something else. What do you see here? This is a bright reflection, right? Where you can see is okay, this area here is okay, all this here is relatively darker, right? So what did that tell you? That this is produced by, okay, as a strong reflection. What you have here is mainly as okay, produced by something which has a weaker reflection. Or a lower amplitude. Okay, so yes, okay. B mode stands for brightness. Okay, and is the basic for all ultrasound scanning. So B stands for brightness. It also stands for basic. Because what you will realize that whenever you turn on the system, the mode that is always going to be on is your B mode. You can't turn that off. So B is not only for brightness, but also going to be as okay, the basic mode off. It's also going to be the basic mode off ultrasound scanning. Clear, okay? And as you just looked here, as okay on the picture that I just showed you, I just put the colors there to just okay demonstrate different things. But otherwise, yes, okay, what is it? It's pretty B as in boring to look at. Right? Okay. Very as okay, plain, black and white, or boring to look at. Did you guys get that? Okay, now please don't tell that okay as B more stands for boring. But okay, guys. Any questions? Any wise words of wisdom? No? Okay, guys, do you mind giving me 5 minutes?
Go for it.
Okay, thank you, my dear. Okay, guys, thank you. That was a lifesaver. Okay. Okay, guys. So any questions? So what are we left with? The last mode. M mode, my mode. M stands for motion. Okay. Now, guys, please, that's okay. When do we want to use this mode here? To check on something, scan something which is that is in motion. Why? To check or just okay, scan the degree, or we can say it's okay, extent of motion or movement. Right. Now, guys, out of all the structures that you guys may be scanning, that kidney, which picture I showed you earlier, is that kidney going to move? No. Clear. Okay, so you probably just okay won't be using M mode on that. Okay. The thyroid. No. Even if a baby is moving, yes, okay, you're not going to just okay use M mode. Okay. So this mode here is okay, primarily is okay, is going to be used for echocardiography. Yeah. To me, that's okay, check on the motion or movement of the walls of the heart and the valves of the heart. Did you guys get that? Now, if you guys recall the other day, yes, okay, I use yes, okay, M mode to display yes, okay, the motion of okay, yes, or the movement of the contraction of the muscles and the yes, okay, in the palm of my hand when I move my thumb. Okay, so in M mode, yes, okay, what you will have, you will still have okay as a regular B mode image. Did that make sense? That the concept is the same. A bright reflection or something that appears bright is because it was okay as a reflection with a strong amplitude. Whereas if something is okay appear dark, it was mainly as okay because it was due to as okay a reflection produced by a lesser amplitude. But what you then saw below that was what we called M mode. And if you look here, guys, that's okay, this M mode, sorry. I'll just make this a little bit more clear or cleaner out of this. This is going to be as okay where we have our M mode. Which is going to just, okay, let's just get off with the two axes. Because the y-axis is going to be as, okay, depth. Or we can say it's, okay, the depth to the reflector. Whereas M mode, the other axis that we have is the x-axis. And what the x-axis is going to just, okay, display is going to be time. Did you guys get that? Very mainly says, okay, and we can mainly say now, for time, guys, this point here is going to be the 0 point. So we can mainly says, okay, then, okay, as we go here, yes, okay, just going to be older and older and older and older and older and older and older. Reflections produced by, yes, okay, the moving structure here. Whereas in the y-axis or along the y-axis, this is going to be shallow depth. And okay, this is going to be deeper. So as we go from here to here to here to here to here, there's just going to be greater and greater and greater and greater depth, just as we had in the regular B mode image. Did you guys get that?
Yep.
Okay, dear guys. Now, if you recall from your B mode image, let's say that, okay, this here is our B mode image that we have here. Okay. Now, if you recall the other day, yes, okay, there was a line like this. And which I say is okay was going to be as okay one single pulse. Okay, and what this one single pulse here is going to be doing is, because it's okay, recording the motion, which over a course of time is going to just okay be displayed like this. But what is that we see here is, so let's choose a more color. Which means yes, okay is going to just okay be displayed along this plane here. But from shallower depth to greater depths, where okay, over the course of time, the motion that happens in the structure here let's go. Just okay, I have some example. In our image, this, then we first, we can say it's okay, even. this. We could say this, and then we could say, let's just use this one. Let's say this reflector. Okay, so the motion that happens in, let's say it's okay, this reflector here, at this point here, over the course of time is going to be displayed like this. Likewise, okay, yes, the degree of motion of this reflector here, or this structure here, over the course of time is okay, is going to be displayed like this. And likewise, the degree of motion of this reflector here over the course of time is going to be displayed like this. So here we can say, okay, this structure is going to be, okay, mainly be a structure that has a greater movement, the greatest movement. This one here is, okay, let's say it's, okay, has the least movement. And, okay, let's have a lower movement. And, okay, yes, this one here is going to have, okay, at the less motion, for instance. And that's why you see us, okay, here there's, okay, the graph is very small. Here it's, okay, we have a greater graph, and whereas, okay, here we have okay, a greater graph, but over the course of time. Yeah, okay. So that's how we can say it's okay that the y-axis still is going to be the depth. Depth of what? Depth of your reflectors. Where you can say it's okay, this is going to be the shallower reflector. This will be deeper. This will be the deepest. Okay, there's x-axis mainly as, okay, represents time. But what is that we see here? Mainly as, okay, just the motion of these three structures here. Okay, in this area. As I said the other day as well, that, okay, if you want to, you can actually just, okay, move this single pulse over here. And what is that they will do then? Main is, okay, show you the degree of motions of these three structures here in this area here where your graph may change. Did that make sense? Or if you wanted to, yes, okay, you could move it over here. But this was going to be, yes, okay, that one single pulse. Clear? Okay. And why is it that we need, yes, okay, one single pulse? Because that single pulse mean is going to give us, okay, what we can call a great sample rate. Did you guys get that? Okay. So, ladies and gentlemen, one thing to take with you for chapter 13 is that when you want to, yes, okay, check on things that are in motion, you want a high sample rate. Clear? Okay. Now, guys, this sample rate here is going to, yes, okay, be not only brought up in chapter 13, but also, yes, okay, being brought up in chapter 19, which is your Doppler. Okay, in which we mainly as, okay, will be as, okay, looking at, okay, as the flow of blood or checking on the speed of blood. Okay. But these sample rates here are mainly going to be using one single pulse. Because if you had more than one pulse, let's say it's okay here. Look here, guys. Okay. Let's just say that, okay, yes, our P transducer here had 5 or 4 PCTs. Right now, we set this one here as using the pulse, or being the pulsing one, to make us, okay, check on the motion of our moving structures and producing that in a graph. Had it been, let's say, 2, what would have happened? First, this had to go and come back, and then this will fire and come back. Then this, and then this. So what happens? As this one here was checking, this one here was lagging behind. Okay. So that line that you may, yes, okay, see, yes, okay, across your B mode image is going to be, yes, okay, that single pulse that is going to, yes, okay, check on the motion of the structures along the course of that pulse. Okay, so that single pulse, or we can say, okay, lower number of pulses is going to just, okay, give us a high sampling rate. Whereas, okay, if we go in the opposite way and say, it's okay, greater number of pulses is going to lead to a low sample rate. Or have any of you ever been to a place where they give out free samples? They want to promote, yes, okay, something that they're selling, right? Clear, okay. Now, if you are the only pulse there, or let's put it this way, just one pulse. What that mean? It's okay, you were standing there, you were the first in line, and there was nobody else. So what could you do? Just pretty much, okay, pick up as many samples as you want to, and it's okay, eat them, right? So what are you able to do? You can say, it's okay, all dependent upon, it's okay, how quickly you were able to just, okay, chew and swallow whatever the samples was of. That's okay, you can have a greater sample rate. Okay, because you were the only one in line. Now, if it was that, okay, there was a big line behind you, and they said, well, okay, listen, well, let's say it's like a short line. You could pick up one sample, take that, but then the rule was, okay, we want a new sample, well, okay, you have to go in the back of the line. That was a small line, yes, okay. You will get back to the desk after a shorter period and, okay, get a new sample. Whereas, okay, if that line was long, what was going to happen then? It would take you a longer time. So in that case, that's okay, your sample rate would be low. Did that make sense? Okay. So here is, okay, what they do is that they use one of the many pulses as a sample pulse. Or if you look at your second last paragraph in your book on page 162, please highlight that. We can even read it together if you guys want to. the paragraph that says, yes, okay, since M mode ultrasound arises from a single penetration into the body. The sample rate of high mode is very high and is equal to the pulse repetition frequency of the system. So what would be a sample rate or sampling rate? The number of pulses per second by that single pulse. Did you guys get that? So sampling rate is just going to be as okay a way of saying how many samples did you get in a minute or second, for instance, whichever. Now just go back to your Costco line and yes, okay, apply that. If you are the only one, yes, okay, you can go like this. Okay. Whereas, okay, if it's something that everybody, a lot of people want, yes, okay, sample off, then okay, they're going to be yes, okay, a greater line. And you may have to wait, yes, okay, 3 minutes before, yes, okay, your turn comes back for a new sample. Did you guys get that? So please highlight that paragraph. Okay, guys. So any questions about, yes, okay, the axes? X-axis is time. Y-axis here is depth. Okay. I just keep that okay as a common standard, guys, whenever you have a graph. And when time is one of the parameters displayed on that graph, it's usually going to be as okay along x-axis. Did you guys get that? Okay. Now let's see. Okay, guys. Can you guys see this?
Yeah.
Okay, guys. So without much of a discussion, what is this? This is mainly as okay, your regular B mode image. Is that clear?
Yeah.
Good. Okay. Where we can say, okay, this is good. Oh, sorry, let's just choose another color. We can say, okay, this here is going to be as okay what we have here. And then yes, okay. These here are going to be as okay what we have here. Clear. Okay. We can even see the depths. This depth equals this depth. Dip depth equals this depth. And this depth equals this depth. Did you guys get that? Okay. But this graph here, guys, this graph here, that is actually, it's okay, your M mode. So this will be depth. And this here is okay, will be time. Now, guys, what I mean is, okay, I'm just going to do for 1 sec is zoom in on the B mode. Yeah, okay. This here was just, okay, our regular B mode. Okay, and what we mainly see here is, okay, yes, we guess it's okay, different chambers of the heart. And okay, as what we have here is going to be, okay, mainly as, okay, valves. But that's not what I'm going to just, okay, focus on here. But what you see here is there's a dot, there's a dot, there's a dot. There should have been a dot up here, but that's fine. We can say it's okay, even it's okay, a dot here in this case. What do they represent? When you connect these dots, that's going to be as, okay, your pulse. Right, okay. So what did that tell us? Mainly it's okay, because this line is okay, the connection of the dots run here. That is mainly as, okay, going to be as, okay, whatever structure that moves along this line here. That will be displayed on our image here. Did that make sense? So we can mainly say, okay, this motion here mainly is, okay, maybe this. Okay, what we have is, okay, up here. Maybe this. And we go as, okay, slightly deeper, less, okay, as this here, it maybe as, okay, it's going to be the motion of this. Oh, sorry, of this. Up and back, up and back, up and back. And so on. Okay, you can even say, okay, here, this is a bright refraction. And okay, the even is, okay, label here, okay, pericardium. Did you guys get that?
Yes.
Okay, so what is it that we see here? That, okay, that there's a great degree of motion over the course of time of this structure here. Whereas, okay, as there is, you can say it's okay saying a lesser motion of this structure here. Because, okay, the difference between the peak and the bottom, the top and the bottom, the top and the bottom, the top and the bottom here is great. Whereas, okay, if you compare it, okay, here, the difference between the peak and the bottom, the top and the bottom, the top and the bottom is less. Over the course of time. So it's okay. Here was recorded. There was a great distance between your transducer and let's say it's okay, the structure here at that point of time, which means it's okay, just changed because this structure here had moved. So that now the distance was less between the transducer and the reflector over the course of time. Did that make sense? Clear? Okay. Now here is okay, your depth of the reflector since we talk about it, okay, in terms of a pulse, is going to, yes, okay, have a different PRP. Any questions? If you travel a shorter distance to reach your goal and come back, it would take you less time, right? Whereas if you have to travel a greater distance to reach your goal and come back, it will take you greater time, right? Here we go. So whether you physically or practical, actually it's okay, run between point A, B, and back to A. Or if you do that running in your head. Clear, okay. Please don't run back and forth, it's okay, when you're taking your tests. Anyways, that's why I say do that running back and forth in your heads. Okay. But that's how you can mean it's okay, simplify, try to, it's okay, correlate this to, yes, okay, day-to-day things. Whether you think about it or not, that's okay, but anything that happens on day-to-day basis involves physics. So what were the takeaways for today? Over 3 modes. What did the individual letters mean? What did the what axes did we have in the modes? What was it that each axis represent? And okay, yes, just general facts. A mode were for ophthalmology, B mode, any kind of basic or regular or boring scans is going to be B mode. Clear, okay, that B mode can be, yes, okay, superimposed by other modes. One of the modes that we saw here was M mode. Okay. But when we mean it's okay, just got a something that okay has looked like a graph. Oh yes, okay, where that along the y-axis, I mean yes, okay, just the depth between the transducer and the reflectors. That's okay, was changing. And the greater the movement, the greater the change in that depth, the greater was going to be as okay, the movement of the structure here. Yeah, okay. Did that make sense? And please highlight that second last paragraph on page. What was the page? What? (162). Sense M mode. Okay. and I show you that single pulse. In some cases, okay, we dots just as we had in the picture. In some cases, okay, maybe a line as we saw it on our system the other day. Okay. But whatever way it appears, that's okay, how you be able to move it right to left, up and down, so on, so on, so with help of your mouse. Okay. Now, guys, a similar thing is going to, okay, reappear in chapter 19. Clear? So what did it here tell you? Yes, okay, the sampling rate. Out of all of the pulses being sent out by your transducer. Because of course you're going to have pulses to produce an image. But one of those pulses besides, okay, producing an image will also be used to measure or count on the movement. Did you guys get that? So sampling rate is a term that you will hear again. Yep, okay. And when you hear the word rate, it's going to be as okay, something per time. So something or anything per time is going to be frequency. Oh, yeah, as you could say, it's okay, the pulse repetition frequency. Okay, guys. What day is it tomorrow? Tuesday? It's so for this week here, we may be striving to look towards the next chapter, which is going to be chapter number 12. Okay. And I may be jumping. Okay, that's, you don't need to. I'm recording.